Hello, Frederick. This is Hongwei, and I was a student of the PWC Wireless Communication in 2009, and this is the lab that I haven't finished. And the reason I didn't finish during that time is I have been doing this for 3 times, and we have the hardware problem, and I already have all the code in place 2 years ago, but I didn't have the chance to present this to you in the lab. Probably today I can explain the things I did, but without the lab because I don't have the IT++, I don't have all the system ready. So instead, I will use the board to show how I understand the project and to explain how I will do this step by step. So now we come back to this project. The title for the project is to transmit data via the wireless channel between PCs or anything. So basically, the things we are going to do is that we given two PCs, and between the two PC, we are going to transmit a voice file via the wireless network. So the first step that I do that, I will transmit the voice because the voice file into the digital file. Because in our wireless communication, we are only able to transmit bits, which means we can only transmit the digital stuff. So that's why we have to transmit everything, a picture or voice, whatever we have, to digital data, which means bits. It can be 1 or 0. So the file in the end will be a vector with 1, 0, 1, 0, or 0, 1, so something like this. So after doing this, for this one, I know there was a function in MATLAB and in F++, it can be called automatically. I will show you later in the code, and you can check my code. This is what I did. So it transmits these things to be a digital file first, we do like this. And now we move to the first step. In order to transmit this one via wireless channel, we need this information to be robust enough. Because in case one of the signal, if one of the bits is not received, then we cannot get the correct information. So in order to avoid this information, we do a lot of things to increase the robustness. And the most important one that we use, and also I use in the code, that we do the coding. Coding itself is just to increase the redundancy of the source code. If we call this 1010, we call this one as a source bit. And this contains all the information we should have for the voice. After have coding, we want to have this one more robust. The way we do it, we give more redundancy. For the most simple way that 1, instead we transmit 1, we transmit 111. We transmit 3 times. Instead of transmit 0, we transmit 000. Which means even we have 2 bits we cannot receive, still we can get the correct information. So we increase the probability to succeed by 3. But this means we have the code rate be only 1/3. So all of this will be a coding algorithm. But in my application, I just use a traditional convolutional coding. There you must need to have the code rate. Also, you have to give the gain vector. If you have the code rate gain vector, I think you can just apply for the function in the MATLAB or the X++. You can get the convolution coding easily. So we won't come to that detail, so this will apply it. So it gives 3, and it comes output of the coding. For example, we say the output from 1010 come to be 11001010. You see, this means half code rate. So 4 bits come to 8 bits. So now we come to next step. We want to transmit this 8 bits. Still, we have a problem because in the real network, when you're transmitting something, you might have kind of channel dip. In that case, you probably will lose consecutively several bits in a row. In this case, if you lose this 4 bits in a row, then we will lose these 2 source bits, which means in the end we cannot decode these two bits. So the way we solve it, the way we to avoid this kind of frequency dip, we do interleaving. Interleaving. It's not that fancy for interleaving, actually. The only thing we do for this one is simply that instead we transmit 1, 1, 0, 0, 1, 0, 1, 0, we format this one to be a different matrix. If we do like this, 1, 1, 0, 0, 1, 0, 1, 0. Instead we transmit in this way, 1, 1, 0, 0, 1, 0, 1, 0. We transmit in another way. So we transmit 1, 0, 1, 1, 1, 0, 1, 0, 0. In this way, even we have 3 bits in the row that we cannot decode correctly, but in the end, you probably will not receive this one, or this one, but still you can decode the information to get the source bit based on the decoding algorithms. And one more thing we need to keep in mind that we must make a matrix, and then we just shift between the column and the row. And if anything left, we use the 0 to fill the padding. So after interleaving, the source code will be present in a different way, something like this. So the simple example that 1, 1, 0, 0 will become to 1, 0, 1, 0 because it do like this. 1, 1, 0, 0 it come to 1, 0, 1, 0. So this is what I did for the interleaving, and this is how it's working in theory. And after this one, we come to the real transformation actually. We start to move from the bit to the pulse. Because as we all know, when we transmit something, you cannot say that you transmit one bit. Everything will be based on this. You transmit a signal, you transmit a wave, and the different power, different phase, or different frequency, it carry all the digital information. So everything will come to the pulse in the end. And one of the things that can show by the pulse is phase. Have phase or pulse. You have different things. So based on this theory, we come to a next step. It's the modulation. The modulation here is simply we want to rephrase the bit to another information, and the reason we do this is for capacity. Instead, we transmit bit by bit. If we transmit one bit with one pulse, one signal with one bit, this is called BPSK, which means one pulse can only transmit one bit. But we want to increase capacity. We want to transmit more than one bit with one pulse. So where we solve it? In QPS, for the example, this one can be BPSK, QPSK, 16 core, or even 64 core. All of this is based on the phase. So we will come to this later. And in the lab, in my code, I use QPSK. I only use this one because Q means quarter, which means instead we transmit one bit with one pulse, we use one pulse to transmit 2 bits. Like this. These 2 bits together will come to one pulse. The way we achieve it, we just use different phase. It's like this. If we want to transmit 1, 1, it's here. If we transmit 1, 0, it's here. If we want to transmit 0, 0, then it's here. If we transmit 0, 1, then it's here. This one we can say have the phase 0, phase 90, phase 180, phase 270. They have different phases, so we can decode in different way. So to make it easier, it's like this. If you see the real thing, 1, 1 will be replaced by this. Start from 0, phase 1, 1 0 will be replaced from 90. 0 0 will come to something opposite. Minus 90 and 0 1 will come to this. Yeah. So this is what QPSK is doing. And if we use IT++, they have a function called QPSK modulation. So you can just have an input and you call that function, you got output. If I use MATLAB, they don't have this kind of things in place if you don't buy the special plus. But then the easier way is like we just have the 2 bits formatted and we replace 1 to be this value, 0 to be minus. So then still it's normalized by 1. And we take the first bit as a real and the second bit as a complex domain. So then 2 bits can be 1 symbol and with 1 real domain and 1 complex domain. So that's how the QPSK will work. So that's how I worked. I simply call the modulation function in the IT++, but this is the things I can still do if I don't use IT++, and that's the basic for QPSK. After this one, we've got a symbol actually. Instead of the bit, we got a symbol, and symbol will contain 2 parts, real part and complex. So when we come to this, we close to do the real transformation. But in order to further increase the capacity, we use OFDM. It's a very old technology and there's a lot of background behind. But the only thing actually technically we do is that we just do the inverse FFT. This itself is very complicated, but if you take this one as a box, we have a lot of applications in different software. We can call this function, and with this kind of symbol input, modulated symbol input, we can get the output. And this output will like this. We need 3 other inputs. We need to know, I can say 2. We need to know how many subcarriers, number of subcarriers will be needed for this one. I will be back to this later, what it means. And also we want to know how many carriers want to be cyclic shift, which we use for the protect between the interference, inter-OFDM symbol. So then how this one will be used? What's the meaning of number of subcarriers? It's like this. After OFDM, you will got the signal in frequency domain. So let's make this easier. So actually you will have a lot of subcarriers. You sum up them together, you come to the OFDM symbol. And 1 subcarrier in frequency domain will carry 1 symbol at the end. So by doing this one, if we say this is 64, I use 64 in the code, and also the cyclic shift is 16. So in total, we have 80 subcarriers, but only 64 can be used to carry the digital information, which means 1 OFDM symbol have 80 subcarriers, but can only carry 64 symbols. So from this one, we come to this kind of complex picture, but we just ensure all of this is 1 subcarrier. And all of this will carry the symbol. And the first and the end will be used with the for the guard. The things used in between will be used to transmit the data, but it's not really located in between, it's all complete. But as we can see that not all the subcarrier can carry the information. That's the key I want to say here. So after this one, I can clean this one. After this part, we just give an input, as I did in the code, you can see. We give the number of subcarriers, we give the number of cyclic shift, and then we come to the output, and this one is the OFDM symbols. Now we try, and this will be the symbol we transmit, and this will be the symbol received by this antenna. So I think this, for now, I think we come to the first step, how should the transmitter should do for this one. But we have one more thing we need to do before we really transmit this signal. First, we need to know the channel input. Because when we transmit this one via the wireless channel, the signal will get degraded because we will have the interference, we have the fading, so the same power will be changed. So when we transmit something, and when we receive, the power will be different. So you will hear different voice. In order to avoid this one, we need to do channel info estimation. At least we need to know how many dB the power will be decreased. The simplest way to do this, we will have the barcode code. I cannot remember the barcode code with the details, but I can explain a little bit. This is the barcode I use 111100110101. The fancy part of the barcode is that when you have the transmit something in the barcode, and if we do this kind of multiplexing, you will get a very clear pulse in the middle for the barcode. So we use this one to do channel estimation. So this barcode code will be added on top of OFDM symbol. So after we got this OFDM symbol, a lot of this state, we will add the barcode code just before this one. So when the receiver receives the symbol, it will take the first barcode code and then it will scan to get the power of the barcode code. We know how much gain we will transmit for the barcode. This will be cited, and this will, if we transmit 5 dB for the barcode, and when we receive this one, if you see receive 1 dB, we know all the signal will be degraded by 4 dB. So that's how we use barcode to estimate what's the channel for the real symbol. So that's the barcode I use here. Besides the barcode, there's one more thing we will do, because coming to here, it's only the symbols. If you want to transmit, we must transmit on a certain frequency. The way we should do it is that we need to multiplex the symbol in the frequency domain. So then this will be moved to a higher frequency. It's like this. If I have a like this, this is our current symbol. We want to transmit in a higher frequency. This is the frequency domain. So by multiplexing another frequency, which is like cosine something, then this one will be moved to the higher frequency, and we just transmit the signal with higher frequency. By doing this, we will have more bandwidth to transmit the data. So in this case, in the end, I multiplex the thing to the frequency, and then I transmit this signal. Transmit. So all of this part is done in the file PWC2 transmitter. So all of this should be done by transmitter, and transmitter will have the voice data to be OFDM symbol plus barcode plus barcode at a higher frequency transmitted. And as a receiver will do everything symmetric but opposite. So when the first receiver receives one, it have to use this pen to here to multiplex with the frequency again. So here, come here, If you multiply the same frequency, so we move the thing from the high frequency to the lower frequency. And then if you do the FFT for this one, so we will change from the subcarriers to FDM symbol. When we come this one, we have the real part and complete part. We change all of them. We do demodulation from QPSK to be a base. And then we do de-interleaving. We just do the same thing because we made the matrix again, and then we shift between the column and the row. So we will get the interleaving, we got this one. And then based on our coding algorithms, we can get the decoding. By doing decoding, we got this real data, and this will be recorded by the IT++ player to play the real voice from this kind of data. So all of this is the process we did from the transmitter to receiver step by step. Even I didn't mention the clear code, but I think I explained how each block should work and even how this should be coded. So from this, probably you can see how much I understand this project, and you can judge if I'm qualified to fulfill this, qualified to pass this lab, or if you need any more information, if you think anything didn't make clear, let me know. I will do it. And as you remember in the lab, there's one last thing I need to mention, because we don't have this pulse actually. We don't have this one in the any kind of programmer, not in Atlas, not in the MATLAB either. So we will fix a pulse by do sampling. So in my code, I use 200 sampling to represent one pulse. So it means when we count one OFDM symbol, instead we have one symbol. Actually, we have this kind of sampled pulse to present the OFDM symbol. So that's something I added as well. Before I real transmit it, I do kind of convert from digital to the non-digital. Yeah, that's all the information I want to show you, Frederick, and be free to ask any question you want. And attached, I will have the full code in the email. So thank you anyway, and I'm highly appreciative for all your help for me. So thank you.